So our next speaker, Xinyun Chen, who's in the School of Data Science at the Chinese University of Hong Kong in Shenzhen. Xinyun got a PhD in operations research at Columbia University back in 2014, which is not that long ago. So in Australian terms, we would still call her an early career researcher. But despite that, she's got a bunch of really good papers, and it's clear that she's on a pretty good career path. And so it's my absolute pleasure to introduce Xinyun, and she's going to tell us about online learning and optimization for queues with an unknown demand curve and service distribution. So thanks, Xinyun.
Thanks, Peter. Thank you for the nice introduction. So today I want to talk about one of my recent work on online learning for queuing system. The talk is based on the joint work with Xinyun Liu from NCSU and my student Gui Hong. So in this work, we want to explore whether the recently very popular online learning method can be applied to solve queuing control problem. And in addition, what kind of extra benefit can this new approach brings to queuing problems compared to the conventional approach. So let me start with the introduction. So we consider a very classic or fundamental setting. So in which we have a service system and the customers need to pay in order to get service. So for the service provider, she wants to balance the trade-off between the revenue received from customer, the cost paid for maintaining the service capacity, and the service quality she can provide to the customer. So in particular, we consider single server queue the most fundamental model, probably in queuing theory. We consider MG1 model. So in this model, each customer pay P units of service price, and they arrive according to a Poisson process with a rate lambda P. So basically, lambda is the arrival rate to the system, and also it reflects the demand of the customer and their sensitivity to the price charged P. And the service times, we assume they are ID general distributed and scaled by the so-called service rate mu. So V is the random variable describing the randomness in the service time, and the expectation of V is 1. And to maintain the service capacity at rate mu, the service provider needs to pay a price, a cost per unit of time, C mu. So in summary, the goal for the service provider is to minimize this objective function, which reflects the cost or minus of the revenue she could receive per unit of time in long term. So the first term reflects the revenue received from the patient, from the customer in 1 unit of time. So it's price multiplied by the arrival rate of the customer. Second term is the service cost paid per unit of time. And also we would penalize the service provider if she keep the customer waiting for too long time. So we have an extra term with a coefficient H0 multiplied by the expected workload in the system in the steady state. So this is the object function for the service provider, and she has two control parameters for the system. One is the service capacity, the other is the price to charge to each customer. And her goal is to find the optimal mu and p in certain region to minimize this cost function. Okay, so that's the model and the control problem. So in this setting, we consider the classic MG1 system. So if all the parameters are known, then we can use the textbook PK formula to compute the the workload process in workload expectation in steady state. So this is just the classic PQ formula. Rho is the utilization of the queuing system, and the CS squared is the variance of the service time distribution, normalized the service time distribution V. Okay, so everything is fine if the parameters are all known exactly. We consider the case that in real application, usually you do not know the system parameter prior. You need to, for example, estimate the parameters in the data. Then if we apply this PK formula directly, we will have this, we call this curse-off accuracy in heavy traffic. So for example, if we consider the case, exponential service time, so CS equals to 1, and the service rate fixed mu, and the system is in heavy traffic, lambda is close to mu. In this case, if we increase the lambda by a very small number, say 0.5%, okay, then the expected workload process in steady state will increase hugely by 99%. So this number is just obtained by using this PK formula, plugging the numbers there. Okay. So in other words, if we estimate lambda from data, okay, this indicates that if we have a small estimation error in the lambda parameter, this will cause a large estimation error in the waiting time or in the workload performance measure, and will lead to a large loss in the queuing control. Okay, so back to the previous example, the specific objective we want to minimize. So if we have this kinds of demand function, a larger demand function, and the linear cost, and we can scale H0 so that this is the penalty on the waiting cost. We can scale H0 such that the optimal solution to the previous problem is in heavy traffic. Okay. So in this case, if in each system, assuming that unfortunately we estimate, we have 5% of estimation error in the function lambda. Okay, this picture shows the relative loss in the final in a final decision in the revenue caused by this 5% estimation error. And you will see that when the true optimal rho is close to 1, and this loss in revenue caused by the 5% estimation will grow rapidly. And also the relative loss is much larger than the 5% in the estimation error in the arrival rate. And this is largely caused by the estimation error in the steady state waiting time, or in the steady state expected workload, caused mainly by the 1 minus rho term here in the denominator in the PK formula. Okay, so this is our first observation in this simple problem. Like the conventional approach works well when the parameters are all exact. But if you have some small estimation error in your parameter, and then this nonlinear relation between the queuing performance and the parameter could manifest this estimation error, leads to large loss in your final decision. Okay, so the conventional approach, when the parameters are known, usually is, we call this predict then optimize approach. So we use some offline data to estimate the model parameters and take the estimated parameters as the true parameter, and then make a decision based on your estimated parameter. So we just illustrated that because of the nonlinear linear form of queuing function, and this approach actually requires very high accuracy in the parameter estimation. So in other words, in the stage 1, you might need to accumulate a large data set in order to get very accurate estimation on the, for example, on the arrival rate, especially the relationship between arrival rate and the price P. So in this talk, we investigate an alternative approach, the online learning approach. One benefit of this approach is that to start optimize, this approach does not need like a large offline data set. It can gradually optimize the queuing control utilizing real data time in an online fashion. In addition, like in the predict then optimization approach, we separate the data estimation part from the optimization task. In the online learning approach, in the analysis framework, we account for the estimation error in the ultimate decision-making task. So we have a better relation between the estimation error and the performance of the final decision. Okay, so probably because of these two benefits, online learning approach has been successfully used in many other disciplines of operations research. For example, in inventory control, revenue management problem, dynamic pricing problem, and etc. Okay, so this graph just shows like a standard diagram of online learning approach. Okay, but we want to point out that online learning for queues is not just a quick extension of standard online learning algorithms, like in other areas of operations research. So here I list like some key differences between the usual setting of online learning algorithm and the setting of queuing systems. So first, the state and reward in most online learning settings are bounded, but in queuing systems, for example, we have waiting times, we have workload process. In many standard models, they are unbounded and continuous random variables. And also, like most online learning algorithms works in discrete time because it's in nature it's an iterative algorithm. So it divides the time into discrete time steps, and the system also involves in discrete time. But in queuing system, the system involves in continuous time. And lastly, like the algorithm is a data-driven algorithm. So the optimization is made in using the data. So the property of the data is also very important. In standard online learning algorithm, people usually assume that given the current decision, conditional on the decision, your observation of the data or the system performance under the current decision, the data are ID and unbiased. But in the queuing setting, because of the stochastic dynamic of queuing functions or queuing processes, given the current decision, the queuing data is sequentially dependent. Like the waiting time of this customer depends on the waiting time of the previous customer. And also, we have transient bias because of the transient behavior of queuing system. So the data is not unbiased. So there are a lot of difference between the typical setting of online learning algorithms and the queuing setting. So if we want to apply online learning to a queuing system, we need to treat with these unique features in the queuing setting. Okay, so what we do in this work is that we develop a model-free online learning algorithm for the pricing and the joint pricing and the capacity sizing problem for MG1 queue, which I introduced previously, in which the demand curve, the lambda p, is unknown, and the service distribution is also unknown. We prove that our algorithm has a theoretic regret bound of order big O of squared T log T, which is comparable to other algorithms in like dynamic pricing with unknown demand. And we also check the efficiency of our algorithm using numerical experiments. And the design and the analysis of the algorithm is based on careful statistical studies of queuing data, especially to treat the sequential dependence in the data and the bias in the data. And the statistical studies is based on ergodicity analysis of the queuing processes. Our work is related to first the pricing and capacity sizing problem, which has been studied a lot in the queuing literature. And probably the model we started is most close to the sequence of works by Li and Ward. And our problem is also related to demand learning or dynamic pricing with unknown demand. So there are like a vast of literature in this direction, especially in the area of revenue management. So I just list a few classic, most representative literatures on dynamic pricing for single product. And in their works, they prove that regret bound is in order of square root of T. So our regret bound is compared to their result. And the key difference is that in those literatures, people do not take into account of any queuing phenomena in their decision, just to do the pricing part. In our work, we need to deal with the queuing phenomena. Also, I think our work is closely related to this small but rapidly growing literature in learning for queues. So I just list a few of them. So some of the researchers try to apply reinforced learning algorithms to queuing control problem, and others tried the bandit approach to solve a scheduling problem in queues. And we have a previous work using stochastic gradient descent approach to solve a similar model, but under a stronger assumption that the demand function is known. Okay, and also I want to mention that last year there's a tutorial or survey paper written by Wharton and Xu, covering the recent advances in this specific topic. Okay, now let me introduce the specific model setting and some technical assumptions we need to develop the theory. But later in the numerical experiment, we will relax some of these assumptions. Okay, so just this remind you of my first slide. We consider MG1Q, and we have a two-dimension control problem. We need to decide the optimal service capacity mu and the price P. And the objective is to minimize or optimize the cost rate in the steady state. And we consider setting that the parameter related to the customers are not easy to know for the service provider. So the arrival rate or the customer sensitivity to price is unknown. Lambda is unknown. So here we didn't even assume any function form for lambda. Okay, and the service time distribution is unknown. But we assume that the cost function is known because this is on the service provider side. To carry out the analysis, we need some extra technical assumptions. So the first assumption is we assume that the object function is smooth and convex. actually we derive some sufficient condition that is easier to check, to guarantee the smoothness and the convex of the object function. And we also assume that service time is a light tail distribution. This is in order to get the ergodicity convergence result. And finally, we assume that in the region of your parameter mu and p, lambda p is always smaller than mu. So the system is uniformly stable under all candidate control parameters. Okay. So here are the more detailed assumptions. I want to explain a little bit on the convexity assumption. So we derive some, because it's an MG1 system, so we can derive some sufficient condition to make sure that object function is convex. The condition is not very simple, but it becomes like more straightforward in some special case. So we just list a few like commonly used demand function. And in each demand function, we can find a convenient condition to make sure that the final objective function involving the demand and also the Q-length processes, the whole function is convex. And this is the uniform stability condition and light tail distribution of the service time assumptions. So throughout the theoretical analysis, we will assume these three assumptions hold. But in the numerical experiment, we will relax some of these assumptions. Okay. Okay, now I'm ready to introduce the algorithm. So our algorithm is still in the framework of online stochastic gradient descent algorithm. Basically, because the queuing system involves in continuous time, so we will divide the continuous time into some successive cycles. And roughly speaking, we will observe the system for a while under certain control parameters, and then collect the data, and then use the data to estimate the gradient of the object function under the current control parameter. And based on the gradient estimator, we are going to update the control parameter for the next cycle. Okay, so this is the main idea in the algorithm design. But because we do not know the demand function lambda, we don't even assume any parametric form for this demand function lambda. So we are going to use a model-free estimator for the gradient. We just use the most straightforward finite difference gradient estimator. So in each iteration, we actually need to run 2 cycles. Okay, so basically in each iteration, we will maintain X bar, which is our current guess of the optimal control. And then we will run 2 cycles. In the first cycle, we will run the system under X bar plus some small perturbation. Okay, ZK is a vector because now we have 2-dimension control problem. So we need a vector here. In the next cycle, we will, here is a typo. We will run the system under the X bar K minus this small perturbation. Okay, so finally, using the data in the 2 cycles, we can get the estimation on the object function under the 2 parameters. And because this is a small perturbation, so we hope that the difference between the performance measure divided by the difference will give us, divided by the small perturbation delta, will give us a good estimation of the gradient. So this will give us the gradient estimator on the current optimal control. And then we will do the policy improvement because we are solving a minimization problem. So we are going to update the policy by minus the gradient multiplied by some learning rate. Okay, so in this is a framework of the algorithm. And in this algorithm, we have 3 hyperparameters, delta, tk, and eta k. So next we will use the emphasis will be how to use the queuing analysis to optimize the choice of those hyperparameters so that we can get the best performance of the algorithm. Okay, so now I want to introduce more details on how we estimate the gradient from data in each cycle. And because this is related to the analysis in the queuing dynamics later, okay? So basically, given the data you can just think the data is a trajectory of the workload process in a continuous time and tk. And we can observe the number of arrivals in this cycle. So this will give us the estimator of the arrival rate. And this part is the workload process observed in long time, in continuous time. But we cannot observe the real workload in real time because we do not know the customer service time until they finished their service. So instead, we use some approximate observation to approximate the real workload time. And we just integral this and take the average. This is our estimator for the steady state workload, expected workload. And last, this is the cost function, which is known to the service provider, so that this one can be computed directly. Okay, so you can imagine that the first thing is just the Poisson process. This is a Poisson, which is an unbiased estimator of the Poisson rate. So this one is easier. The most difficult part is here, okay, because this is the transient workload process we observed in finite time. But what we want is the steady state expectation of the workload. So there are some bias in this estimation. And also you might notice that we have a coefficient alpha here. So we are going to discard the data in the beginning of the cycle and at the end of the cycle. So I just illustrate the dynamic of the system under the online learning algorithm here. And so in the previous cycle, this is the illustrated dynamic of the queuing process. And as time goes by, it will gradually converge to the steady state, okay? And then the next cycle starts. So we need to update a control parameter. So for the next cycle, we will start from a transient state. And as time goes by, we hope that the queuing process will get closer to the steady state under the parameter of the new cycle. And we will, to estimate the mean workload in steady state, we will discard data in the beginning of the cycle. We call this warm-up period to reduce the transient error. And we will also discard the data at the end of the period because in this period, the newly arriving customers haven't finished their service. So for this period, our estimator on the workload process is not very accurate because of the delay observation of customer service time. So we'll also discard the data here. So we will just use the data observed in the middle of the cycle to estimate the steady state workload process. Okay, so this is the first design in our algorithm. So the performance of our algorithm, because this is an online algorithm, we do estimation and optimization at the same time. So we will measure the performance of this algorithm using a regret, which is like a standard performance measure for online learning algorithm. L is the total number of iterations, like the iteration of the gradient descent. And it's defined by the actual performance, expected actual performance of the system under your online learning algorithm by choosing a decision parameter for each cycle, okay? Minus the performance of the algorithm, of the system under the optimal parameter, okay? And because we are doing a we are minimizing the cost, so you can expect that the optimal performance is smaller, always smaller than the actual performance of the system under your algorithm. So this regret is a positive quantity, and the better the algorithm, the smaller the regret. So we want that we can minimize this regret in our algorithm design. Okay, so given the framework of this algorithm and the performance measure, the next we want to do is very clear. So we want to properly chosen the 3 hyperparameters in this algorithm to minimize the regret bound. And of course, the one of the key components in our algorithm is the finite difference gradient estimator. So the algorithm performance will depend on the finite gradient estimator. And so we will use the bias and the variance of the gradient estimator to bridge the hyperparameters and the regret bound. Okay, so here's the definition of the bias and the variance. Basically, they describe like a conditional on the current decision, how far is the gradient estimator from the true value of the gradient. Okay, so next we need to do careful analysis on the bias and the variance of the gradient estimator in terms of those hyperparameters. Okay, and in the last step, we will connect the regret bound with these 2 quantities, and so that we can build a connection between the regret bound and the 3 hyperparameters, and then we can choose our hyperparameter by minimizing the regret bound. Okay, so we first start with the bias of the gradient estimator. So a lot of calculation here. So I just want to highlight to you that there are 3 components in the bias of the gradient estimator. The first, of course, is the finite difference estimation error. But this part is easy to deal with. It's just delta k squared. The other 2 parts, the first one, the blue part, is caused by the error of delayed observation. So we will deal with that using that we discard the data with large delayed observation. The other part is the transient error. This is caused by the fact that the observed data, the observed Q length is not stationary. There's a difference between the observed transient Q queuing process and the steady state queuing process. So we call this part the transient error. And this part we will control it using some ergodicity analysis of a single server queue. Okay. We first deal with the error caused by delayed observation. So I think because of time limitation, I will omit the technical details. the high-level idea is that our estimated workload process exactly equal to the true workload process if the workload process at time t is smaller than the cycle length minus time t. In other words, this means that the current customer in the system at time t, they all have finished the service before the end of the cycle. So we can recover exactly the workload at time t. Okay, and so this error can be bounded by the probability that the workload is larger than this t. And we then use the fact that service time is a light tail and the system is uniformly stable. So we can bound this error by an exponential term of the distance to the end of the cycle. So this is how we deal with the error caused by the delayed observation. Next, we need to deal with the transient error, which is caused by the difference between the observed workload and the steady state workload. So to do this, we basically use the fact that the workload process will converge to the steady state quite fast. Okay, but to get a finite time error bound, we use a synchronized coupling technique. Basically, we couple the workload process with a stationary version and show them that the two processes will coalesce in a while. So we also get exponential bound on the transient error. Means that the workload process will converge to the steady state in an exponential rate. Okay, so that's come back to our design algorithm. We discard the warm-up period to deal with the transient error, and we discard the end of the data close to the end of the cycle to control the error of delayed observation. Okay, so based on the previous analysis, we can find a closed form upper bound for the bias of the gradient estimator in terms of the algorithm hyperparameters. Okay, so in this way, we finish the analysis on the bias of the gradient estimator. Next, we need to do the analysis on the variance of the estimator. I apologize again for those very complicated formula, but the two key components in the variance part is, again, we have this error caused by a delayed observation. We will deal this part using the same idea previously. Another part is caused by the sequential dependence in queuing data. So because remember that HK is like the integral of the observed queue length. They are not ID, they are dependent data. So when we sum them up and take average, we will have the autocovariance in the final estimator. So we need to deal with the autocovariance of the workload process. So to deal with this, we don't know whether, to the best of our knowledge, we are not aware of any previous literature analyzing autocovariance of queuing data. So we prove a new lemma to bound this autocovariance. What we the proof technicals again using synchronized coupling. So basically, we couple to compute the autocovariance for the workload process observed at time t and time s. We will couple the workload process with a stationary version starting from time s smaller than t, independently with w. And and use this to to bound the autocovariance. So again, we will find a nice expression of the autocovariance bound, which is also exponential in terms of the difference between the two observations and the distance from the first observation to the beginning of the cycle. Okay. So again, we plug in the autocovariance bound and the bound on the error of delayed observation. We'll get a nice bound on the variance of the gradient estimator, again, in terms of the algorithm hyperparameters. Okay. So in this way, we finish analysis on the gradient estimator. So using this result, we are ready to get the regret bound for the whole algorithm. So roughly speaking, the regret has three components. The second component is standard in online learning algorithm. This is the regret caused by the suboptimality of your control parameter. The first component is somewhat unique to queuing system or other system. This is caused by the non-stationarity of the system performance. And the last component, we call this regret of exploration. This is caused by the fact that to estimate the gradient, we actually do not operate the system under our guess of the optimal parameter. Instead, we add small perturbation to help estimate the gradient. Okay, so our previous analysis on the bias and the variance will mainly be used to bound the regret of suboptimality because they are related to the convergence of the gradient descent iteration. Okay, so due to the time constraint, I will omit the details. So plugging the previous results and the non-stationary error, we follow the approach in our previous paper. And the regret of exploration is straightforward. So sum them up, we will get an expression of the regret in terms of three letters ABC, which actually is the order of the three hyperparameters, T as tk equals to k to the order of a, etc. Okay, so using this expression, we can do some optimization, find the optimal choice of ABC to minimize the order of the regret bound. So in this way, we get our choice of the parameter. So the cycle length is in order of k to the 1/3. The finite difference parameter is k to the order of -1/3, and the learning rate should be should be to the order of 1 minus k. So this is the choice of our hyperparameter. And plugging back those hyperparameter into this equation, you will get the order of the regret bound. So this is the final result. We give the choice of the hyperparameters, and this is the regret bound in terms of the number of iterations. And note that we can also evaluate regret in terms of the running time of the algorithm. And if we evaluate this in the running time of the algorithm, we will get a regret bound is in the order of square root of t with some extra log terms in t. So this is our final result on the regret bound. Okay. So in summary, we have designed an online algorithm for a queuing system with a no demand function. And theoretically, we can have a regret bound, upper bound guarantee, which is almost of order square root of t. So next, we are going to validate our results and also test the robustness of our algorithm using a bunch of examples, numerical examples. So we first start with MM1Q because in this case, we have the true optimal parameter so that we can compute the regret. Okay, and in this case, all the theoretic assumptions are satisfied. And here is the result. Basically, we hope that the log of the regret and the log of the should be a time, log of the running time, and they should be covered by a straight line with slope smaller than 0.5, because 0.5 is the upper bound, theoretical upper bound for this slope. And we have another example in which actually the condition, the technical assumption that f as convex is not satisfied. But in this case, numerically, we found the algorithm still works well. And the slope of this log-log fit graph is smaller than 0.5. So remember that in the very beginning, we actually motivating this study using the so-called curse of accuracy in heavy traffic. So we test the performance of our algorithm when the true optimal parameter goes to heavy traffic. And we also test the performance algorithm for different service time distributions in terms that the service time distribution have different levels of dispersion. Okay, so this graph shows like the performance of the algorithm when the optimal row goes closer to 1 and under different service time distributions. And we can see that the algorithm in all the cases, the 0.5 upper bound still hold, and also the magnitude of the regret does not deteriorate dramatically as the system goes to heavier traffic. So we think this answered the very first question we have. This algorithm works well and is robust to the heavy traffic regime. And the last experiment we do is in the theoretical analysis, we have been focused on the MG1 model. We want to see whether this algorithm can be extended to general renew arrivals. So in this experiment, we consider system with renew arrival, but just exponential survey, so that again we have the theoretic solution to compute the regret. So in this setting, we found numerically this algorithm also works well, and the slope of the log-log line is smaller than 0.5, indicating that our approach probably can be extended to more general GG1 setting. Okay. And so in summary, we developed a model-free online learning algorithm for MG1Q with unknown demand function. And we get the algorithm with theoretic guarantee on the upper bound of regret. And it's numerically efficient, especially in the heavy traffic regime. And our analysis combines ergodicity theory of queuing process and the framework of regret analysis for online learning algorithms. So we believe this approach or this framework can be extended to other models if similar ergodicity results hold. For example, probably immediate extensions from single server queue to multi-server queue. Okay? And as a newly developed area, we think there are a lot of future interesting direction to explore. So for example, currently we only focus on the most fundamental model in queuing theory. So in the future, there are a lot of extension, and we can include more realistic customer behaviors in the system, like abandonment, bulking, and etc. And from the theoretical side, there's an interesting direction to lose the technical assumption. For example, we assume the system is uniformly stable. So if we remove this assumption, this is related to so-called safe online learning. in which the algorithm can be smart enough so that it can identify which region is safe for the system, which region is unstable for the system. And also, we assume that the object function convex, although it's generally true for a lot of interesting examples, but in more general setting, we hope we can use some recent advances in stochastic optimization to remove this assumption so that this approach can work for more general non-convex objective functions. Okay, so that's the end of my talk. Thank you very much.